Good afternoon. Today's lesson I want to go over more examples on Fourier cosine series. We will move later on to Fourier sine series, so basically the same idea but in terms of sine functions. So basically the idea is to represent a function in terms of a series of sine functions, and then there will be a combination of these two. I will go over a couple of examples for the purpose of insisting more on the meaning of these series and their properties, and in particular what they actually represent beyond the interval 0 pi. And then of course later we're going to extend it to any generic interval, because by the way there's nothing special about this 0 pi. So what I just wrote here is just a brief summary of what we covered before, right? So we say that the function f has a cosine series representation given by these terms on the interval 0 pi, this representation, these coefficients which will give you this representation, are given by this formula. An is equal to 2 over pi, the integral from 0 to pi of f of x cosine of nx dx, where n is 0, 1, 2, 3, and so on. Nothing special with the interval 0 pi. Well, I guess what's special about it is that this is kind of the interval that gives you a neat representation. Typically the terms are a little bit less tedious, but it can be any other interval, and the formula is very similar, the idea is similar, which means when we move on to a generic interval we will not spend as much time as we spent on this introductory part with the Fourier cosine series, because lots of these ideas will be repeated later. So I'll mention this later on as well, but as we move along in the material, in some aspects we will need to say a little bit less because the idea is the same and we will focus just on the new part. But without further ado, let's move on with one extra example. So let's actually represent or compute the Fourier cosine series of a discontinuous function this time. Last time we computed, let's write it here as well. So last time we computed together the representation of x in terms of a cosine series, Fourier cosine series, which was pi over 2 plus 2 over pi summation from 1 to infinity minus 1 to the n minus 1 over n squared cosine of nx. You're going to have these representations in formula sheets, so you don't have to write them one more time. I just want to put it here just for myself. So let's say I want to find, as another example, let's say I have a function f of x which is, like I said, a piecewise defined function. So let's say it's equal to 1 on the interval 0 pi over 2, and then 0 on the interval pi over 2 and pi. You would notice here I use strict inequalities because the points of discontinuities are not actually that important when you come up with these series. The series will exist even if the function is not even defined at all at those intermediate, those discontinuous points. In the vast majority of cases, the series will converge to a value even if x is equal to pi over 2, in this case a discontinuous point. But we'll talk about more of on the convergence of series later. I just want to mention that whether you take, let's say, less than or equal to pi over 2 on that branch or not, that's actually not important at this stage. It doesn't affect the series for this function because when you integrate, those discontinuity points won't matter. Again, this is because these are jump discontinuities, so the sided limits exist and are finite. That's the main assumption, right? So this should be a piecewise continuous function. All right, so let's find the Fourier cosine series for this one using the formula, this one here given in this corner. And I want you to pay close attention to the moment when you should realize as you move along, if that's the case, whether you actually have to take some cases separately. When you can start with a generic n, which initially can be any value between 0, 1, 2, 3, and so on. But when you move on with the integral, you may realize that some cases must be treated separately. Because, for example, you may have over n or something else similar, in which case, for example, the case n equals 0 should be treated separately. So that depends on the problem. So let's start with the formula. So an is 2 over pi, the integral from 0 to pi the function itself, right, cosine of nx. Now, because the function is 0 between pi over 2 and pi, then this integral can be taken only between 0 and pi over 2, right? Because you can split this between 0 and pi over 2, the integral, right? And then from pi over 2 to pi, but because the function is 0 in that interval, then that second integral is going to be 0. So basically, in effect, you're left with 2 over pi, the integral from 0 to pi over 2, the function itself, which is 1, and then cosine of nx dx. So this will be actually a very easy integral, right? And notice at this moment, when I integrate cosine of nx, so the integral of cosine of nx, if you do a quick mental substitution, is sine of nx over n. At this moment between 0 and pi over 2, at this moment you should realize that the case n equals 0 should be treated separately. So you can't assume n is from 0 to infinity, right? I mean, this is valid only for n equal to 1, 2, 3, and so on. Because you cannot divide by 0. So this is the moment when you realize that the case n equals 0 must be dealt with separately. All right, so let's finish up this integral here. That's going to be 2 over n pi sine of n pi over 2 minus sine of 0. And so let's leave the answer right now in that form. So this is 2 over n pi sine of n pi over 2. And let's do the case a naught for n equals 0 separately. So we save this for later, and then now a naught, going all the way back to the original formula, that's 2 over pi, the integral from 0 to pi over 2, right? Because again, between pi over 2 and pi is 0, 1, and then cosine of 0x is going to be just 1, right? So cosine of 0x dx. So basically that's just the integral form of 1 dx between 0 and pi over 2. Antiderivative is x, and then if I plug in pi over 2, I get 2 over pi times pi over 2, which gives me 1. Okay, so let's write down the full answer. So my function is equal to, as a Fourier cosine series, is equal to 1 over 2. Pay close attention here. Remember, the formula is written in such a way that the first term in the cosine series is a naught over 2. If you forgot why, just go back to the previous video and I explain why we have this little gimmick, so that we have a simple single formula for the coefficients. So don't forget that extra over 2 once you compute a naught. That is only the case for the cosine series. Okay, so because a naught was 1, then f of x is equal to 1 over 2. And then everything else we can write it in a summation from 1 to infinity of an, which was 2 over n pi sine of n pi over 2. That's the coefficient. That was what an was. And then cosine of nx. Be prepared because we're going to use tables of Fourier cosine series later and many other series. And it is very... I mean, it could be confusing in the beginning if you're not prepared to realize that some of these series can be written in various forms, basically because of algebra manipulations. I don't personally care one way or another, so if your answer is correct in a test, you can leave it as it is. But if you compare, for example, your answer to the answer given, let's say, in the back of the book, or even in the problem itself, some of the problems will give you the answer. And then you're just responsible to go through the computation. Be prepared to do some algebra manipulation to actually check to see if you get the same thing, because often your answer is correct, but in a vastly different form just because of various algebra manipulations. So for example, at the very least, you will see often in the book any constant that is inside the summation to be pulled out of the summation, like 2 over pi in this case. And then there's that annoying -1 cycle through that may appear sometimes. in the in problems like this when you have sine and cosine of n pi, because for example n pi over 2, if you think about it, it cycles through between values 0, 1, minus 1. I'm not going to bother to waste time with this, but you'll see often this summation written differently, going through the parity of n, whether it's even or odd, because again, if you look at the trigonometric circle, so as n goes from 1 to infinity, so it starts with pi over 2, right? So n equals 1 means sine of pi over 2, n equals 2 means sine of n pi, 3 pi over 2, and then again 2 pi, and so on. So even multiples of pi over 2 will be 0. So if n is even, then sine of n pi over 2 is gonna be 0. And if n is odd, then sine of n pi over 2 will cycle through minus 1 and 1, or 1 and minus 1 in that order. And then you can rewrite this whole summation by disregarding the even coefficients, and you can write only the odd coefficients. Again, my strong opinion is that this is just far more tediousness than it's actually worthwhile, especially if you have to combine these series with others, and then it's better to just have the values of n be consistent, like from 1, 2, 3, and so on. I don't think it's a big difference, but be prepared that in the tables you may see the same thing in equivalent form. Let's actually remember what this represents. Remember, this Fourier series doesn't just give you the function that you start with in the interval 0 pi, but it will also represent the even extension of the same function. So let's remember what that is, starting with a graph of the function itself. So the function was 1 between 0 and pi over 2. So let's say this is pi over 2 and this is pi. And that's the value of the function 1. And then 0 between pi over 2 and pi. So because the cosine function is even, the same series will cover, first of all, the reflection over the y-axis of the same graph. That means the even basically function corresponding to the other, to the left half of the interval. So between minus pi and 0. So it will cover this shape as well. So I'm going to make it thicker like that so you can see it. And then the same shape, this same precise shape, repeated over a period of 2 pi, because the period of the cosine x is 2 pi. So basically, it will cover the extension, the periodic extension with period 2 pi of the same graph. So you can think of what you see between minus pi and pi as the shape that is repeated left and right. We're not going to deal with this too much, but I'll show you also with Maple how this series actually covers this graph as we write more and more terms. This is kind of cool actually, because one thing to notice here is that although the function itself, the original function, is discontinuous, the Fourier series, or let's say the Fourier polynomial, right? I mean, if you stop at some number of terms in the series, you're not polynomial, I'm sorry. So if you start at a fixed number of terms in the Fourier series, that's going to be a continuous function. And that continuous function approaches basically this discontinuous function as you increase the number of terms that you add in the series. I'm going to comment on this when I'll show you the example with Maple. And for the Fourier sine series, to anticipate a little bit, the idea will be the same, except we're going to figure out the representation of the function in terms of a sine series. And like I told you before, try to be patient, because it's not going to be obvious at this point what's the connection with partial differential equations, but I promise you that in a number of lectures all of this will come together. and you'll see why this tool, actually the Fourier series, is needed in solving that partial differential equation problem. Okay, so let's stay tuned for the next page for more example and discussions. All right, so let's do another example. This time what I like to call a trivial example, though why it's trivial may not be so obvious unless you think carefully beforehand. But for now, let's just blindly go with a formula, and then only in retrospect we should think about and realize that maybe we could have guessed beforehand why the example was trivial. So let's say I want to find the Fourier cosine series of the function f of x equals 1. But unlike the previous example, 1 just on the interval 0 pi. So that's a continuous function on the starting interval. And again, pay attention how the formula works, right? So the formula again for an is the 2 over pi, right? So the goal is again to write this function as a series of cosine terms. Make sure when you go over this to write down any comments or questions you may have. There will be plenty of questions in the beginning until you get used to the whole concept. So it's very important to write down questions and prepare them to ask them during the live meetings. So 2 over pi, the integral from 0 to pi of the function itself, cosine of nx. So because the function is equal to 1, then I just have to integrate cosine of nx dx. Once again, once I integrate this, I realize that the case n equals 0 needs to be treated separately. So the integral of cosine is sine, so it's sine of nx over n. As long as n is 1, 2, 3, any number, any natural number besides 0. And notice that, surprise, surprise, this time around all the coefficients, at least except the first one, which we'll compute it later, but all the other coefficients seem to be 0. Sine of a multiple of pi is 0. Once again, refer back to the trigonometric circle. If you hit multiples of pi, 0, pi, 2 pi, 3 pi, and so on, the sine value is equal to 0. Sine of 0 is 0, so all the coefficients are 0. Now, obviously, they cannot be all 0 because, after all, I'm representing the function f of x equals 1. And at this point, you guys should probably guess what the first coefficient is. In fact, take a moment and see if you can guess what that value is of a naught over 2. And let's actually confirm that it's that way with the formula. So a naught follows the same formula, 2 over pi, the integral from 0 to pi, 1 times cosine of 0x dx. Cosine of 0 is 1. The antiderivative is x. Make sure I'm not hitting this part here. Pi cancels and a naught is equal to 2. A naught is equal to 2, but remember, in the formula, when I write the full cosine series, I have a naught over 2, so it's 2 over 2 plus summation of 0 cosine of nx. So basically, as a Fourier cosine series or on the interval 0 pi, 1 is equal to 1 plus 0 plus 0, 0, 0, 0, 0, 0. So this is actually not a surprise if you look at the periodic extension, even periodic extension, right? Because remember, the Fourier cosine series doesn't cover just the function in interval 0 pi, but the even periodic extension. But in this particular case, the even periodic extension gives you still the same constant function 1. So you start with the function equal to 1 on the interval 0 pi. You flip this over the y-axis. So then between minus pi and pi is the constant function equal to 1. And then when you extend this over other intervals of length 2 pi, well, it's still the same constant function equal to 1. So the periodic even extension is gonna be the constant function. One. So of course all the other coefficients will be 0 for cosine because the first term essentially is identical to the function. I would like to compare this situation to what you learn in calculus 2 about power series. So for example, let's actually write a detour here. Let's make a detour on calculus 2. In calculus 2, you had various functions that you could write as power series, right? So for example, 1 over 1 minus x is this infinite sum of powers. But then what could it be, for example, the power series for x squared? Well, it doesn't take much to realize that the power series for x squared is going to be basically 0 plus 0 plus x squared plus 0, right? All these coefficients 0 except the one that is x squared. Because x squared, basically, the function that you want to represent as a power series is one of the terms in the power series. So in a similar manner, the function that you want to represent as a cosine series is part of the cosine series. So, for example, take a wild guess and think about what will be the Fourier cosine series for the function f of x equals cosine of x. Again, at this point, it shouldn't take too much to realize that this is going to be a 0, the first term, plus 1 times cosine of x, plus 0 times cosine of 2x, dot, 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 and so on. And in fact, just for fun, just for practice, let's pretend we don't realize this beforehand, and let's apply the formula. So in this case, the formula for cosine of x will be, for the coefficient, for the Fourier coefficient, will be 2 over pi integral from 0 to pi cosine of x cosine of nx. We'll see later if we have to exclude some of these values. And at this point, there's a trigonometric formula that we have to use, which you don't have to memorize, but I'll write it down so you know what I'm talking about here. Cosine A cosine B is 1/2 cosine of A plus B plus cosine of A minus B. We need to use this formula so we can integrate that product. So that 1/2, I can take it outside, and then inside the integral is cosine of the sum of the two. So that's x plus nx, which is 1 plus nx, plus cosine of x minus nx, which is 1 minus nx dx. 2 cancels. And then let's integrate. Again, a u substitution in your mind. That's going to be 1 over 1 plus n sine of 1 plus nx plus 1 over 1 minus n sine of 1 minus nx between 0 and pi. And at this moment, you realize that you need to exclude the case n equals 1. That needs to be treated separately because you can divide by 0. Any number 0, 2, 3, 4, and so on will do, but not n equals 1. And when you plug in pi and 0, you just get 0 everywhere, right? Because again, any sign of any multiple of pi will be 0. So that means all the coefficients are 0 if n is not equal to 1. And if n is equal to 1, I know already it's going to be 1, right? But let's check. Let's do this separately. So a1 equals, we go back to the formula, right? So if n equals 1, is going to be cosine squared x, right? Because it's cosine times cosine, so that's cosine squared x dx. And notice how much price you pay if you actually didn't realize beforehand that it has to be 0, because cosine of x is one of the Fourier terms. Because now what? Now we have to use the double angle formula, right? Which is in this case 1 minus cosine of 2x over 2 inside the integral. So we can integrate it. So that splits into the integral of 1 over 2. I hope I can fit this. I don't want to move on to the next page for just for this. And then minus, I break this into two integrals, and then minus 2 over pi, the integral from 0 to pi, 1 over 2 cosine of 2x dx. Okay, the first integral will be, so 2 cancels. The first integral is x between 0 and pi. And the last integral will be 0 because, again, 2 cancels. Because the antiderivative is sine of 2x over 2. And when you plug in 0 and pi, it's going to be 0, right? Sine of 2 pi minus sine of 0. So you're left with 1 over pi times pi, which, as expected, it's equal to 1. So the reason I went over this example is, again, to encourage you to not forget, never give up on your judgment, essentially, when you look at these problems, because often the answer is much easier if you do that way, right? I mean, if you need the Fourier cosine series for cosine of 3x, let's say, once you recognize that's one of the terms in the series, that function, then you realize that the other coefficients should be 0. And I'm going to add another example. I want to comment to just give you a preview of coming attractions in terms of formulas, in terms of manipulating Fourier series already given to you in the table, because that's what we're going to do for the most part. You are expected to be able to compute a Fourier series with formulas, but in practice, you seldom do this because it takes too much time, and it could be a very difficult problem to do by hand, to compute these integrals. So that's why we use tables of Fourier series. So stay tuned for the last page. Okay, so you will see table of Fourier series in this course. I mean, we were going to work with a couple of tables with the more usual series. Not too large. There are far larger tables in practice. But since we focus on learning the concept, we will essentially cycle through some usual functions. Kind of not that complicated. I mean, the problems can be tedious even as they are with these simple functions. But we'll keep on using these simple functions because of convenience. So how do you actually use these tables in practice? So, I mean, first of all, if you're lucky to have a function in the problem that coincides with the one in the table, you just use it. Just be aware that you will have these various forms. So like I said before, for instance, in the table, you will see, for instance, the Fourier cosine series for x given by this formula. And as you notice that the summation cycles through only the odd coefficients, because the even coefficients are 0. But remember, when we obtained these together with the formula, we got that x is pi over 2 minus let's see, make sure I don't not minus. So x was pi over 2 plus 2 over pi summation from 1 to infinity minus 1 to the n minus 1 over n squared cosine of nx. So, and again, it's the same interval, right? It's very important, if you missed this discussion from last time, to take a moment, don't rush, never rush in the beginning, take a moment and understand that these are the same. It's just algebra, nothing fancy than that, nothing fancier than that. These are just the same, except that the second form goes through all coefficients from 1 to infinity, including the zero ones, and the first form excludes the zero coefficients corresponding to the even coefficients. So if it's not clear yet, notice that minus 1 to the n minus 1, it's actually minus 1 equals minus 2 if n is odd. So that extra minus 2 comes out and it's multiplied by 2 over pi, and that's why it becomes minus 4 over pi. Make sure you understand that, because if your answer doesn't go through this algebra trick, you may think that your answer is incorrect if you compare it with what the problem says or what the table says. Once again, it's not like you have to change the form. I mean, if you're confident that your answer is correct, you can leave it in this form, in this second form. But if you want to check with the answer in a different form, you have to do some algebra to make sure it's correct, or you made a mistake, because it's not that obvious. So in practice, we could and let me actually give another example from the table. Often various series are given in terms of on a generic interval. So for example, x squared has the following representation on the interval 0c. So c squared over 3 plus 4c squared over pi squared, summation from 1 to infinity, minus 1 to the n over n squared, cosine of n pi x over c. So for example, if I want, right, so that's given in a table. If I want x squared as a cosine series, let's say on the interval x2, then I just replace c equal to, right? Nothing fancier than that. So c equals 2, so that's maybe 2 squared over 2, 4, 2 to the power 2, pi squared, and pi x over 4. And maybe if you want, you can do some simplifications. 4 over 2 is 2, the first term. Then it's going to be 16 over pi squared. I forgot the cosine here, so that's cosine of n pi x over 4. This is the stuff of work we're gonna do. This is the type of work we're gonna do later in the applications, right? We're gonna use the tables, not directly the formula of computing the coefficients. One extra thing I want to mention is that sometimes the function that you want to come up with is a combination of functions given in the table. So for example, let's say I want to find the Fourier cosine series on the interval 0, let's say 0 pi for 2x minus x squared, let's say. And I should say, this is basically the type of questions in which it's really disadvantageous to actually write your series by omitting some terms, because it's kind of hard to combine them with other series. So I would rather use the second format that we obtained together. So what I want to say is that if the table gives you the Fourier cosine series for x, and then for x squared, then you can so if your function is a combination of this, a linear combination of this, then you can come up with the Fourier cosine series by simply plugging in the series for x and x squared in the problem. So basically 2x minus x squared is 2 times the series for x, which you can get it from the table, minus quantity the series for x squared, which again you can get it from the table. And from this point on is just tedious algebra steps to make it more compact. And let's do it together. So the series for x let's put it in parentheses. We computed together. That was pi over 2 plus 2 over pi summation from 1 to infinity minus 1 to the n minus 1 over n squared cosine of nx. And then minus the series for x squared, which we obtain it over here. That's 2 plus 16 over pi squared summation from 1 to infinity minus 1 of to the n. I gotta take that back, I'm sorry, because I set the interval 0 pi. Let's see if I can fix that. Yeah, because I have to replace c with pi. So let's see, because in the previous case I put the interval 0 to let's see, I think I'm going to do it on the second page. So let's do it on the second page. All right, so on the interval 0 pi, x is this, we obtain it together, and for x squared, replace c with pi, right? You have the formula for 0c. Let's replace c with pi, and if we do that and if we simplify also, so x squared is going to be pi squared over 2 plus 4c squared over pi squared. C squared will cancel now with pi squared because, well, let's write it down so it's clear here. So when I replace c with pi, I get that. And then summation from 1 to infinity minus 1 to the n over n squared cosine of nx, right? Because pi over c becomes 1. See, that's why actually it's easier with c equals pi, because pi cancels with c in all of these terms. In preparation for combining this, right, so the goal was to find the summation, the Fourier cosine series for 2x minus x squared. You can bring in these constants now inside the summation, because those summations will be combined later. So it's 2 over n squared pi minus 1 to the n minus 1 cosine of nx. And x squared, pi squared over 2 plus summation, my pi squared cancels, 4 minus 1 to the n over n squared cosine of nx. All right, so finally now when I combine these, so 2x minus x squared is 2, like I said, the series for x minus the quantity, the series for x squared. I get 2 times pi over 2, the summation from 1 to infinity, 2 over n squared pi minus 1 to the n minus 1 cosine of nx, and then minus the quantity, the other series. By the way, you should pause and go slower than me. I mean, I go faster so that it doesn't go too long, the video, but it's very important to take your time to go about this. Not so much to simplify later, but to visualize this clearly as a series so that you can identify the coefficients. To write it as a Fourier cosine series, remember there is that constant term on the outside. So now we're going to combine these terms, right? So it's 2 times pi over 2 coming from, we're going to distribute the 2 here, and then we're going to distribute the minus as well. So 2 times pi over 2 minus pi squared over 2. That's the first term. And then when we combine the summations, there's going to be a big term here multiplied by cosine of nx. So look carefully. When you pull cosine of nx, you're going to have 2 times 2 over n squared pi. That makes it 4 over n squared pi times minus 1 to the n minus 1. And then minus the other term from the other summation, 4 minus 1 to the n over n squared. And it's perfectly fine to leave it like that. If you like and you think you have enough time, you can maybe do some little algebra to see if you can maybe make this shorter. What's actually important for our class is to compute the coefficients. So basically you have to, at some point in the process of solving the PDE using this method, to identify what that coefficient is. Whether it's simplified or not, it will be needed in the problem, right, to write down that coefficient. Sometimes to make it easier, you can maybe denote it and say, okay, I get these results where an is whatever you got in that parenthesis. With a simplification, you may have to do it again to check the answer with maybe a book answer, right? And in this particular case, I don't think actually it's too much stuff you can do. You can pull 4 over n squared, but it doesn't seem to be too much of an advantage. So again, you can leave it like that in an unsimplified form. Maybe, cancel this 2 and that's it. But again, that's how you come up with other series from the table. And I think that's it for today. I'll see you later.